podcast. So today we are going to discuss another topic. We have here the shear and deflection. Okay. So in here, the shear as the member bends, shear stress occurs because of the changes in length of its longitudinal fibers. For positive bending, the lower fibers are stretched and the upper fibers are shortened. On the other hand, for a negative bending, the lower fibers are being shortened and the upper fibers are stretched. So to illustrate that, if we have here a beam that has a positive bending, okay, so say this is our neutral axis. Notice that the upper portion here is shortened because this is subjected to compression, and we have also a stretch on the lower fibers. Now because of that, the shear stress will be developed on our section. Okay, so likewise, kapag meron tayong negative bending, okay, say this is the neutral axis, the lower fibers in here will be shortened and the upper fibers will be subjected to stretching. Okay, so in our strength of materials, recall that the shear stress on beams is equal to VQ all over IB. V here is the stress on the distress section. Q here is the static moment of area about the neutral axis. I is the moment of inertia and B is the width of the shear at distress. So in here, in steel, talking about I section or flange section, this formula shall be simplified to tau is equal to V all over the web area. Now in steel, the strength of the shear stress is denoted by FV, wherein FV will take it from 60% of the yield strength of our steel section. So FV is equal to 0.6 of Fy. Now if we are going to substitute in here, in this equation, tau is actually the strength in shear, so that is equal to 0.6 of Fy. Hence the right hand side of the equation remains to be V all over web area. Okay, and then cross multiply, this will now become our nominal shear strength, that is 0.6 of Fy times the area of the web. Now the area of the web refers to this area, okay, in here, the shaded portion here. It is equal to the overall depth times the web thickness, TW. Now this formula is multiplied by CV, wherein CV is the modifier for buckling behavior of the web. For buckling behavior. of our web. Hence, this shall become now our nominal shear strength for the steel. So, therefore, Vn is equal to 0.6 of Fy times AW, or the area of the web. So remember here, we note that the area of the web is equal to the overall depth times the web thickness. Now, we have used to this expression, the nominal, okay, so that we'll be having two procedures, the load resistance factor design and the allowable stress design, wherein normally LRFD is governed by phi, okay. In here, we denote here by the phi by a notation sub V to indicate that this is under shear, and ASD is still omega sub V. Now, in design procedure in LRFD, we always set that our phi times V multiplied by Vn shall be always greater than that of the factored shear, while in the allowable strength design, we always divide our nominal shear strength to that of the omega, okay, in which this shall be always greater than the actual shear on the problem. Okay, so before we are going to have this formula, actually meron tayong CV dito, CV. So ang nadagdag lang actually dito yung CV. So CV is computed on a lot of ways depending on the value of our comparison between H and TW. Okay, so we have here a lot of cases. Case 1, is the condition that when H all over the web thickness is less than or equal to 2.24 of square root of E all over Fy, we're going to use our phi v for LRFD is equal to 1. Okay, so to LRFD. And for ASD, we're going to use an omega of 1.5, and our CV is equal to 1. So this is an instance wherein there is no web instability. Wherein this is normally occurring in most cases that our Fy is less than or equal to 345 megapascal. So in most cases, basta Fy is less than or equal to 345 megapascal, this will fall under this case 1 or under that condition. But still, we need to check our H and the thickness of the web. By the way, what is H all about? So, H, if we have here section I-beam, of course, H is given by this. So this is our H. Of course, in exaggeration kasi we need also to consider here the fillet at the toe of the web. Meron ding fillet at the toe of the web between the flange. Okay? Normally, H is computed by subtracting the overall depth to this dimension. Okay? So this dimension is actually K. Okay? So in the table, this is normally K design. Okay? So that is normally K design. So if we look into a table, okay, so this is actually the spreadsheet on a database. We look into this KDES here under this column. So when we have here a section W21 by 248, its corresponding KDES is 80.5. So if we're going to have the notation, we can see that KDES is the design distance from the outer face of flange to web to of fillet. So as I've been mentioning, so ito yung fillet. Now, if we have a build-up section, say we do not consider KDES or in the problem, we have a fixed depth and thickness. So the calculation for build-up section is simply the depth, the overall depth here, minus the flange thickness. Say this is the thickness of the flange. So therefore, this is calculated H is equal to depth minus 2 times thickness of the flange. While in here, H is equal to the overall depth minus 2 times K. Okay, say K here is the a design distance from the toe of the fillet up to the other side or the lower side of it. Okay. Now, if our ratio of H all over TW would not satisfy this one, or if it is greater, okay, so if the ratio would be greater than this expression, 2.24 square root of E all over Fy, then we have to compute for this expression. Say we compute this expression, square root of KV. So lalabas na dito yung KV times E all over Fy. So what is KV all about? Now, KV here is termed as the web plate buckling coefficient. So, we have two cases here, no? Meron tayong KV for unstiffened webs. And meron tayong KV for stiffened webs. So what is the meaning of this? When we see unstiffened webs, just bear in mind, magkakaroon lang tayo dito ng value ng A. And yung A is the clear distance between the transverse stiffeners. Ito yung transverse stiffeners. If you notice, meron siyang stiffener. So, if this is our beam here, okay, meron siyang stiffener, so that another support will be on that. It will be placed on that. It will be welded on that. So, ito yung mga stiffener. And the distance between those transverse stiffeners is A here. Okay? So, magkakaroon tayo ng a clear distance between transverse stiffeners. Now, for unstiffened webs, we will check the ratio again, this one, each to that of the web thickness. If it is less than 260, we'll just have to take the value of KV equal to 5, okay, for all flange section. But if we have stem of T-shapes, no? Pag meron tayong T-shapes, our KV will be equal to 1.2. Okay. Otherwise, if this would not be satisfied, then we'll have the value of A, no? So A will be proportion to your H. Now, if it is greater than 3, we'll use value KV is equal to 5. So, or an expression to compare A is to H to this expression, 260 all over H all over thickness of the web. Okay. So if this is the scenario, then just the same, we take KV is equal to 5. Otherwise, if this would not be satisfied, no? Ibig sabihin, yung A over H mo is less than 3, no? Or this proportion should be less than this one. H all over TW. Then the value of KV will be equal to this expression, 5 plus 5 all over the square of A is to H. Okay, so those are the procedures for unstiffened webs and stiffened webs. Now, let me put this into the box because this is not yet the case 2 computation, but it is only part of the case 2 calculation. Because as we have said a while ago, we need to compute for KV. Okay? Because KV is included here in this expression. Okay? So, dito na actually papasok yung case number 2. So, in case number 2, we assume that we have calculated KV, no? So, no problem dito because we just have to perform this. Now, there are several subcases here, no? We have a case no web instability, parehas lang sa case number 1. Instability. So this is letter A, no? We take phi. By the way, sa case 2 lahat, sa PASAP na phi is equal to 0.9 and omega on shear is 1.67. Now this is for LRFD and ASD, no? So sa case 1, iba yung value ng phi at ng omega. Okay, by the way, this is ASD. This is LRFD. And this is also ASD. So, see the difference, no? So, magkaiba yung value ng phi tsaka omega in case 1, where we satisfy this kapag ito HTW is less than this expression, no? Now, kapag hindi naman, otherwise, then the ratio H over TW shall be greater than 2.24. We need to compute for this value, and then mafi-fix natin to, itong dalawa, but unlike here, fixed na CV is equal to 1, we need to compute for CV1 on some conditions here. Now, when we say no web instability, we take CV is equal to 1. Diba? Kasi parang parehas lang siya dito. Ang nagkaiba lang is yung phi tsaka omega. So, we need to satisfy this condition if this equation will be met. Yung H all over TW mo is less than or equal to 1.1 square root of ito, yun, expression na KV E all over Fy. Okay? Otherwise, if this will not be met, kung mas mataas siya dito, meron tayong second condition dito sa case 2, wherein this is inelastic buckling. Wherein in here, we take CV is equal to 1.1 square root of this expression, KV times E all over Fy, right? Divided by H all over TW. Now, before we're going to use this one, we should satisfy the equation that 1.1, ito, pupunta mo lang dito yan, no? Actually, pwede na lang natin kopyahin yan. So, this expression here, kung mas malaki nga to, so, magiging ganyang symbol mo, pupunta dito yung HTW. And in here, magkakaroon tayo ng upper limit. For this, we have 1.37 of square root, yun pa rin, ito pa rin, KV E all over Fy. So, pag ito, mas mataas pa rin dito sa upper limit, then that will be falling under letter C. Case 2, letter C. So, case 2, letter C, ito yung tinatawag na elastic buckling. Okay? So, this time, we compute CV is equal to 1.5 times 1.51 times E times KV all over H all over TW. This is squared multiplied by our Fy. So, we have a more complex formula for CV. So, this is the condition na yung HTW mo lalampas na sa upper limit defined in letter B case. Ito yun. Then, we use this calculation. So, I'll just have to highlight this. CV is equal to 1 for this expression. CV is this equation for letter B, and CV will be this equation for letter C condition. Okay. So, that's it. So, ang ano lang naman dito is yung calculation ng CV, right? And these values of phi and omega. So, we have case 1 and case 2. Okay? So, hahaba lang ang calculation natin if it will fall on case 1. Okay? If it would not fall on case 1, then hahaba yung ating calculation kasi dito nakafix lang yung CV sa case 1. So, while in case 2, we have to check this comparison and then adapt what is the category of the buckling effect, whether it is no web instability in elastic buckling or elastic buckling. So, this is with regards to types of shear buckling. Okay? So, if we have this, then we can go back to this formula, no? So, this is the master formula. Actually, ang kino-compute lang natin dito is phi and phi v. Anyway, nakapix naman sa case 1. Mag-iba lang sa case 2. And then sa CV. fixed siya sa case 1 and CV will be calculated more complex under case 2. Okay. So that's it for our shear. So those are just the procedure for shear. Again, the formula is simple. Okay, ito lang ang master formula, no? If we know that, then we'll just have to apply that in our calculation using LRFD and PSD, no? Using those cases. Now, moving on to the deflection. So under deflection, the deflection of steel beams are usually limited to certain maximum values. Among several excellent reasons for deflection limitations are the following. Kasi hindi naman pwede na pasado nga siya sa buckling, shear, and flexure, bagsak naman siya sa deflection because the implication there is excessive deflection may damage other materials that are attached or supported by. So, ano ba yung other materials niyan? It could be a sub-beam or a stiffener beam or flooring, okay, or the floor joist. Then, excessive deflections are likely to cause damage to finishes, partition, and associated structure. So, ito na yung tinatawag nating serviceability because, yun nga, excessive deflection, maraming effect yan, especially to those that of the attached structures in it. So, excessive deflection may damage the principal structural members, which resulted in excessive sagging condition makes the floor area not suitable for future use. Now, I would like to highlight na lahat ng structural members natin are subjected to deflection. So, there's no such thing as zero deflection, no? But, we have to limit that. Okay, so in the code, we have here the allowable deflection in the code. Okay, so for a floor beam, we have here the maximum live load deflection, the maximum dead load deflection, the maximum snow or wind load deflection. So if we wanted to check the deflection provisions, we just have to perform this. So, kung gagamitin mong load, live load, then we have to focus on this column. Now, if you're going to use the dead load, again, focus on the second column, and then snow load, wind load, deflection, ito na. Okay? So, of course, we should take note of the structural elements here. So, ito, you just have to compare this with the calculated deflection according to the loading. Now, there are several methods how to do it, no? But in engineering problems, we have a common loadings, no? Kapag meron tayong concentrated load located at the center, then we'll just have to use this formula. I think you are quite familiar with this formula. So those formulas are actually derived on several methods I'm talking about. Meron tayong MDM method, moment distribution method, meron tayong area moment method, what else? Double integration method, three-moment equation. Okay. So those are some methods in structural analysis to derive the formulas. Again, for the sake of discussion, of course, we'll just have to concentrate with this. So most of the time, a given deflection requirement is a uniformly distributed load. So take note of this formula, 5 WL raised to 4 create 4 all over E I. Okay, so W here is the uniformly distributed load. Okay, so let us try some examples here. Problem number 1, a simply supported beam subjected to a uniform service live load. Okay, so this is the dead load and this is the live load. So we note that our Vn sa LRFD is associated with phi, no? So it should not exceed Vu, no? So in here we have an irregular beam, so we need to establish the shear and moment diagram for us to come up with Vu. Okay? Actually, dalawa yan. Kasi yung Vu, this is a factored load. Yung isa naman sa ASD natin, no? Vn should be divided by this omega V, and this shall be always greater than your load, which are not factored. So in here, I'll just have to concentrate with LRFD, no? Because that is specified in the problem. Now, if we have LRFD, of course, you'll be dealing with our factored load, no? Factored uniform load. See, this is the factored uniform load. W, no? W is equal to 1.2 dead load plus 1.6 of your live load. So if we're going to substitute that, we have 1.2 times 18 plus 1.6 times 30. Okay, so I think this WU shall give us 69.6 kilonewton meter. Of course, warm up tayo, we need to establish here. Okay, so please do not neglect the concentrated load present at that point. And by the way, this 180 here is a dead load, so we need to multiply that by 1.2, no? So 1.2 times 180. So 1.2 times 180 is 216 kilonewton. Okay, so we need to get the reaction. Okay, say this is RA and that will be RB. Okay, so of course we need to note this distance here, 4, and this distance here is 6 meters. Okay, so we just have to take summation moments along RA is equal to 0. Okay, so first we have 216 times moment arm of 4, so that will give us a clockwise moment, and then of course this resultant of our distributed load, this is actually equals 69.6 times 10. Okay, 69.6 times 10, and that will give us a positive rotation, so that is plus 69.6 times 10 multiplied by our moment arm. The half of our 10 is 5. Okay, and then minus ito, yung RB is counterclockwise, that is minus 10 times RB. So we equate that to 0. So therefore, RB will be equal to 434.4. Okay, so for the other reactions, so we take moments along RB and equate it to 0. So this time we are going to have this as our reference point. Okay, so first we have a counterclockwise moment that is 69.6 times 10 times moment arm of 5. So this is negative, counterclockwise, no? And then another counterclockwise moment. So we have here 216 times moment arm of 6. And then we have a positive rotation for RA. Moment arm is 10. So this is equal to 0. So therefore, RA will be equal to 477.6. Okay, so we check that by summation forces vertical is equal to 0. So, having that, lahat ng pababa is first, may pababa tayong 69.6 times 10 plus another pababa, 216. So, this is equal to, this shall be equal to, pataas, yung RA plus RB, 434.4 plus 477.6. So, I think this, both sides will just yield to 912. So, okay tayo dyan. Therefore, we can now proceed to our shear and moment diagram. Okay, so let us have this one, so our shear. First, we have an upward RE equal to 477.6. Or 77.6, and then distributed load. So this area, is 4 by 69.6. 4 by 69.6. So that is equal to 278.4. 477.6 minus 278.4 by 69.6. That is 278.4. We have 199.2 going down here. See, we have this point. Then we connect that by a straight line. So this is 199.2. And we stop in here because we have here the concentrated load going down. 199.2 minus 216 is equal to 16.8. So we have here 16.8. And we connect this by a straight line. Okay, and then going downwards, portion here of our distributed load. Actually, this is 69.6 by 6. that is 417.6 plus 16.8, that is 434.4. 434.4. So we have here the point. So again we connect this by straight line here, and then eventually it will go back to 0 because our reaction is actually 434.4. So in here we'll just have to consider the maximum shear is actually VU, no? So VU is 477.6 kilonewton. So ito yung gagamitin natin dito sa ating LRFB. So also i-compare lang natin tong 477.6 to that of the calculated nominal multiplied by your phi. So una, first, Vn is equal to 0.6 of Fy times AW times CV. So in here, we need to check our ratio of each dot of TW, no? So case 1 muna tayo. Let us see if it would satisfy this expression. Okay, square root of E all over Fy. Okay, so our H here is what? H is equal to overall depth, okay, 688 minus dalawang K, 36.5. So this shall give us 615, no? Okay, so we have now 615 all over the thickness of the web, 13.1. So this will be equal to 46.95 while this expression now, ito is 2.24 times square root of 200,000 divided by Fy is 345. So this shall give us 24.07. So compare natin tong dalawa. We have 53.93. By the way, this is multiplied by 2.24, no? So this is equal to 53.93. So comparing this, therefore, we have satisfied. Oh, mas mataas yun, no? So therefore, it shall fall under case 1, wherein our phi is equal to 1. By the way, phi sa v is equal to 1, no? Tsaka yung CV is also equal to 1. So we are done here na, no? So Vn is equal to 0.6 of Fy AW times CV. So simply, Vn is equal to 0.6 of 345 Fy natin. So yung AW is D times thickness of the web, 688 by 13.1 to 688 and 13.1. This is the area of the web. Okay, CV is 1. So therefore, Vn is equal to 1,865,649.6 Newton. So simply this is equal to 1,865.65 kilonewton. Now phi Vn is equal to 1 times 1,865.65, no? So therefore, phi Vn here is greater than that of our Vu, which is actually this. So malayo siya, no? So malayong mas mataas yung ating phi Vn. So therefore, we can conclude to 477.6 safe in shear. Okay, so that's it for this problem. So moving on to the next problem. So number 2, we have here loadings. First we have ceiling, live load, okay, 120 mm thick concrete, and then 75 mm thick floor finish. So the unit weight is 23.6. So first things first, we need to compute for W, and remember that W is the factored load, because in here we are going to use LRFD. So we have 1.2 dead load plus 1.6 live load. So what composes of dead loads? So first, we have the slab that is equal to the unit weight, 23.6, multiplied by the thickness. This is 120 plus 75. That is 195. So in meters, that is 0.195, and then multiplied by our length 3.6. Now for your ceiling, we have the dead load for ceiling is equal to 1.25, multiply na lang natin ng length to make it in kilonewton. So 1.25 times 3.6, we have 4.5. So ito, 23.6 times 0.195 times 3.6. This is equal to 16.57 kilonewtons. So we are done with our ceiling, and then the thickness of the slab, and then the live load. Of course, we're gonna segregate your live load. So meantime, we total our dead load. We have 21.07 kilonewtons. Okay, so therefore, diretso na natin, W is equal to 1.2 times 21.07 plus 1.6, given live load here is 2.8 multiplied by 3.6. So W will be equal to 41.4 kilonewton per meter. So by the way, this is also kilonewton per meter. Okay, so in here, if we have a distributed load lang naman yan, the maximum shear is actually the reaction, no? So if this is W, so this is L over 2. So symmetrical lang naman yan, WUL over 2. So this is the maximum shear actually. So we can say that VU is equal to W times L all over 2. So W is 41.4 times 3.6 all over 2. We have 7. I'm sorry, this should be 12. I should see. The length is 12. So 41.4 times 12 over 2. We have 248.4 kilometer. Now you might ask, bakit tong 3.6 ang length nito while ito 12? So here's the scenario. Say this would be our beam, no? 12 meters. Is actually carrying the floor having a length of 3.6. So, ito yung 3.6. At ito yung 12 meters. So, this beam carries a tributary length of 3.6 so that it would be transmitted on your 12-meter beam. Okay, that is why lahat ng multiplier natin dito is 3.6. Now, the next thing to do is we check this and then compare it to value 2.24 square root of E all over Fy. So, ano yung ating H? H is D minus 2K over TW. So, our overall depth here is 603 minus 2 times 80.5 divided by web thickness of 27.9. Well, in here, 2.24 square root of 200,000 all over 248. So we'll be having a value here 15.84, and here we have 63.6. So comparing the two, of course, is greater than, so therefore it will fall under case 1, wherein phi is equal to 1 and CV is equal to 1. So therefore, the nominal shear is equal to 0.6 of Fy times AW times CV. Okay, so Vn is equal to 0.6 of 248 times overall depth 603 multiplied by the thickness of the web 27.9. Ito, 1 lang yan. Okay, so lagyan na natin ng phi dito. So 1 lang naman yan. So therefore, Vn is equal to 2,503,366 Newton. So phi Vn is simply 2,503.37 kilonewton, which is very much greater than your VU of 248.4 kilonewton. Therefore, the beam is adequate for shear. So safe in shear. Okay. So moving on to the next problem, we have the third one. Again, this is FY248. So it is mentioned that the length is provided with transverse space at 1/8. So therefore, pag may ganyan, you just have to denote that spacing as transverse spacing, stiffen your members, that is equal to 1/800 millimeters, or this is equal to 1.8 meters. Okay, what else? So what is the value of the design shear strength? The maximum uniformly distributed load that the beam can carry, including its own weight. So all of the properties are given here: the depth, the width of the flange, the thickness of the web. So notice here that wala tayong K, di ba? So therefore, pag walang K, so just have to compute for H as the depth minus 2 times the thickness of the web. So the depth in here is 1603 minus 2 times web thickness is 22.9. So we have here H is equal to, we should have thickness of the flange rather. So this is 2 times 50.5. So 1603 minus 2 times 50.5, that is 1502 millimeters. So again, first things first, we check if what will be the relationship of this comparison of this expression. Okay, so we have 1502 divided by the thickness of the web, 22.9, and then in here 2.24 square root of 200,000 all over 248. So we have here 65.9 and this side is 63.6. So notice na mas malaki ng H all over TW by slight difference. So therefore it will not fall under case 1, no? So hindi na siya case 1, thus it shall fall under case 2. So on case 2, we compute, by the way, pag case 2, our phi is 0.9, no? And kapag ASD, we have 1.67. Ang kakaiba lang dito, hindi fix yung CV natin, no? So CV is yet to be calculated. Okay? So if this is the scenario, we compute for this expression. Square root of KV times E all over Fy. A prerequisite KV here is to be calculated. Ito yung tinatawag na web buckling coefficient. So, it's obvious, no, na ito will fall under stiffened members, no? So, recall that we need to check A is to H, no, if it is greater than 3. or this proportion shall be greater than 260 all over H over TW. This is squared. So if this would be satisfied, no, yung CV natin will just be equal to 5. Sorry, KV. KV will just be equal to 5. So let us check. So yung A natin is 1,800 A over H no. 1/8 all over H 1502. So this is equal to 1.19 or 1.198. Now, itong 1.198 is less than 3. So we cannot adopt this. Otherwise, KV shall be calculated with the formula equal to 5 plus 5 all over A over H. This is squared. So KV is 5 plus 5 all over 1.198. This is squared, no? So therefore, KV is equal to 8.48. So, pag meron na yung KV na yan, you can just compute this expression. So, square root of 8.48. So, this is 200,000 all over Fy. Fy is under 836 till 248. So, we have a value of 82.7. So, anong gagawin natin dito? Of course, this shall be our criteria now in comparing HTW, no? Kapag no web instability, you just have to say na CB is equal to 1 provided that your ratio H all over TW is less than 1.1 times square root of yun, KV E all over Fy. So, another scenario, ito yun yung inelastic buckling. Where CV is equal to 1.1 times yun, square root of KVE all over Fy, provided that HTW is greater than this expression, KVE all over Fy, but not exceeding 1.37 square root of KVE over Fy. Okay. So, lastly, kung ito naman, meron tayong elastic web buckling. Provided that your HTW exceeds ito, no? 1.37 square root of KVE over Fy. Okay. So, ano naman yung CV natin dito? Yung CV natin dito is calculated with this formula. 1.51 E times KV all over HTW. This is squared times your Fy. So, meron na tayong value ng ito, expression ito, square root of E all over Fy, that is 82.7. And I think meron na rin tayong H all over TW. So, ito yun. Ito yun. No? For the first scenario, kapag no web instability, ano ba yung value ng 1.1 square root of KVE all over Fy? So, ito, no? H all over TW, compare it to 1.1 square root of KVE over Fy, no? So, yung HTW natin is 65.9 at ito 1.1 times 82.7. So, dito pa lang mas mataas na, di ba? So, obviously, this is greater, no? So, therefore, sa case 1 tayo, no web instability. Therefore, we can use CV is equal to 1. Pero nasa case 2 tayo dito, wherein yung phi V is 0.9. Okay, 0.9. So with that, we can now go back to the formula of the design shear strength, no? So the design shear strength is actually phi Vn. So your phi is 0.9. Yan yun. Ano yung Vn natin? 0.6 of your Fy times AW times CV. So therefore, VU is equal to 0.9 times 0.6 of our Fy. I think this is 248. Fy is 248. Yeah. So area of the web is the overall depth 1603 times web thickness. Yung web thickness natin is 22.9 here. Okay. 22.9 times CV of 1. No? So, therefore, VU is equal to 5,460,000. So, ito, 5,462.25 kilonewton. Okay, so this is the ultimate shear. So, the value of the design shear strength. So, what is the maximum uniform distributed load that the beam could carry? So, simple na lang to, because VU, for a simply supported beam, we have WL over 2. So, substitute 5,462.25. So, we're getting W, this is 12 meters. Tama ba? Sorry, 8 meters. Okay, we have 1,365.56 kilonewton per meter. Okay, so that's it for the third problem. Okay, so I think for your exercise, I think you should have to solve this one. Just bear in mind that we have here the value of the dead load, and this is the value of the live load. So in our table, in the checking here, of course, the same procedure. We're going to check for your shear, okay? And I think we should also check for your deflection. So for your deflection, it should be noted that we concentrate on the live load, no? Pwede ka ring mag-concentrate sa dead load, okay? But in here, we have the values, of course, what the maximum deflection is this one. Deflection maximum L over 360. But you have to check the deformation using the formula W L4 384 times EI, considering that your W here is live load only. Okay? So yung L dito, just the same, the meters, no, divided by 360. That is your maximum deformation. Now, dapat mas mataas lagi yung maximum or the allowable, sorry. So this is actually the allowable deformation. So hindi pwede na mas mataas ito, this one. Okay. Now, once you have established certain section here from this list here, no? Pag na-prove mo na safe sa shear, no? At bagsak siya sa deformation, what you're gonna do is to select a section which has greater ratio of or greater product ng D times TW, no? So, pag safe sa shear, kukuha ka ng mas mataas na D, T, W, no? At mas mataas na value ng Z. So, what is the indication of that? Zx, no? So, if you have proven na sa calculation safe na sa shear, of course, you do not want to select a member or a section that is lower than this, no? So, once you have established na may safe shear ka at bagsak siya sa deformation, of course, you will consider another section that is greater than this na mas mataas yung DTW so that safe pa rin siya sa shear, check yan, at safe din siya sa flexure. Okay? So, ang magkakaiba lang dito, ang mag-iibang values yung sa deformation because nagbabago-bago yung value ng I. Diba? So, pag nagbago yung value ng I, pag tumataas yung I, therefore, this expression, liliit yan, di ba? So, palit ng palit yan as your I increases, liliit yung value nitong expression. Pwede na siyang pumasok sa allowable deformation. So, madali lang naman yung pag-check ng deformation. Just review it on the uploaded material for you. Now, simple lang, just apply those formulas here and then compare it to the actual deformation based on the loading, no? So, hindi pwede na mas mataas yung actual dun sa allowable. Okay, so that is just a simple principle to deal or to check for your deformation. For the shear, we have the same procedure, no? And for the flexure. So actually flexure was our previous topic before this. Okay, so this shall end our lecture for today. So I hope you have a practice. Thank you and have a good day, class.